All right, it's time. Let's get started here. So the test is a week from today. So I emailed this out. So this is how this will go. 1 week from today, test day. This will be page 1 of the test. I'll have an exam number in here. There'll be an exam number in here. You're going to leave this blank. I'm not doing a seat number. You're going to set your photo ID right there. And you're going to take a picture. You're going to print your name, sign this. You're going to take a picture of this. Where are you going to do that? Right here. I'm going to put test out. There'll be 4, 5, 6 different versions of the test. So I think you should know that ahead of time. The person next to you from it, I'm going to have the same test. You're going to take a picture of page 1, then you're going to put your phone away, and then you're going to go do the test. So it'll be kind of hectic, but you're going to, I don't want your phones out. Your phones can be out down here only, that's it. So you're going to take a picture of page, and what it does is about 4 or 5 people here, they're going to put the wrong ID number on the Scantron. It's going to scan back unknown. 4 or 5 people will go south. I don't know who you are, but once I go to Canvas, this will be an assignment or 0 points. All I got to do is look at the picture you submitted on Canvas. I know exactly what test number you have, and I can match things up. And it's just prevented. It works out great. Like I said, everybody in here, 4 or 5 things are going to come back unknown, or something's going to go around. Right, with this many people. But it works out great. It really does. So again, you're just going to take a picture of this first page. That's all there is to it. Put your phone away and go do the test. Okay, so make sure you got your ID with you. All right, let's see if I can figure this out. Here we go. All right. Let's do number 6. I apologize. I didn't see number 6 up there last time until I went to erase it. So let's look at number 6, and then we'll go with what's on the board, and we'll try to finish. We'll come close to finishing chapter 3 up. So make sure you're printing out chapter 4. All right. So we want an aqueous solutions of silver sulfide. So first of all, in silver nitrate or sodium sulfide are mixed. All right, so sodium sulfide, Na+1, S-2. So this is going to be Na2S. This for sure is aqueous. Sodium, potassium, lithium, ammonium, group 1. Plus silver nitrate, AgNO3. +1 and -1, that is aqueous because it's a nitrate. We get silver sulfide. So this is a double replacement. Sodium is going to take the place of silver. So now listen. This 2 does not come over. This 2 does not come over. It is sodium plus 1. So sodium is taking the place of silver. It's not, there is no such thing as an Na2 plus 1 ion. There is no such thing. It is a sodium ion plus 1. Do not carry this over. What you need to carry over or keep the same is the nitrate. That stays together, the nitrates. So we're going to get sodium nitrate. And that for sure is aqueous plus silver takes the place of sodium. So we are going to end up with silver sulfide. And it says it's a solid 2 silvers. It would look like that. All right, so now we have to balance this pig. And to do that, it looks like we've got 2 sodium, so we put a 2 here. And we've got 2 silvers. We would put a 2 here, and that would do it. Now, they want the net ionic. The net ionic. So we could write out could we write out the complete ionic? We could. But let's do this. We're going to go right to the net ionic. We're making this. We're making silver sulfide solid. What 2 ions make that? These 2 silvers right here. Plus this sulfide right here. So there's our net ionic for that. And you're just looking for one of these, right? You're just looking for one of those. Okay, let's see. Let's do, what do we got? 14. Let's look at 14. What do we got? Okay, 14. So for 14, the thing you should key on right away for 14 is this for sure is oxidation reduction. How do you know? Because you've got cobalt here by itself, so it's a 0 charge, and here it's in a compound. You've got silver here by itself, so if it's a 0 charge, and here it's in a compound. So for sure, this is oxidation reduction, without a doubt. So then the charges are +2 and -1 there. And +2 and -1 there for charges if you want those oxidation states. Now, what is happening? Is this a synthesis reaction? No, because for synthesis, you're only going to get, you're like 2 reactants in 1 product. It is not a synthesis. Is it a combustion? No, for a combustion, you're going to have something like CXHY typically, plus O2, and you're always going to get CO2 plus H2O. The combustion is going to look something like that. Is it a decomposition? It is not a decomposition. Because if it's a decomposition, you'd have AB turning into A plus B. Is it double replacement? No, it's not double replacement. What this really is this is single replacement. All right, so 14. Now we've got 21, or 20, 21, and 22, 20. I think, isn't this the exact same one we did in class? Last time, yeah, is this the last one we did? The learning guide. Yes. This is learning guide, page 17 of the learning guide. Exact same problem. "21. Whoa. This looks like a pig here. Whoa. What do we got here? We got potassium permanganate plus sodium chloride plus sulfuric acid. We get chlorine gas, potassium sulfate, manganese 2 sulfate, water, and sodium sulfate. Which statement is true?" Wowzer. Let's figure this out. What is, let's see if I can do it. What's the charge of potassium always? What's the charge of potassium always? +1. Okay, what's the charge of this oxide? Always -2. What does that give us for a charge of manganese? This gives us -8 because we have 4 of them, correct? This is -8 plus 1, then we got to have a +7, right? We got to have a +7. So we got a +7 there. +1 and -1 for sodium chloride. Hydrogen's always +1 and oxide -2. So what's that give us for this charge of sulfur? +6, right? +6, vertical nods, +6. You got a +6 here. What's the charge of chlorine by itself? 0, right? So right now, I know that chlorine went from -1 to 0. What is that? Oxidation or reduction? That right there is becoming more positive, right? That's oxidation. Which means NaCl is the reducing agent. So chlorine, we're just gonna figure this out and then we'll go to A, B. We'll go A to E here. Let's see. All right. Potassium is always +1 yet, no change. Right? +1 on both sides, no change for my potassium. Oxide here, -2. So this sulfur here is a +6 yet, right? No change on that sulfur. +6. Oxide here is -2. That's -2. Now, manganese, or we got sulfur here as well. Let's see if that sulfur has changed anywhere. Oh, let's see. Let's see if this works. If sulfur stays at +6, what is manganese now? Manganese could be a +2. And then let's see, -2 +1 here, no change.
and -2 plus 1. Whoa, get on here. That means this is still a +6. So if we assume that this is still sulfate through here, this is not the best problem. If we keep this together as sulfate and keep this a sulfate through here, then the charges stay the same for the sulfur. So it looks like, well, it looks like we already have A, but it looks like manganese is reduced from 7 to 2. It looks like manganese is reduced from 7 to 2. Let's see if I can, let's see. So that's my reduction. That means KMNO4, if that's undergoing reduction, is the oxidizing agent. All right, now that I know this much, we've got an answer there, correct? Yeah. We had to answer right away. All right, 22. Let's see if 22, what do we got on 22? I'm gonna try to write out 22 and squeeze it in right here, maybe. Yeah. I'm going to write this out so that it gets a little bit more organized. Okay, let's see what we've got. Hydrogen +1, oxide -2. So that gives me -8 and +2. So -8 +2, I need another +6. So that makes this carbon +3, right? Carbon's +3. Potassium is always +1. Oxide's -2. So that gives me -8 and +2. We only have one manganese there, so it looks like manganese is a +6. -2 for the oxide and carbon dioxide gets me a -4. So we're looking at carbon with a 4. And -2 +1, nothing changing there. Whoa, manganese is changing the way it looks. -2 for the 3 oxides. That gives us -6. So that makes these 2 manganese, each of them a +3. And then we have +1 here and -2. Okay, so now we've got manganese for sure, +6 to +3. And what else? Carbon is +3 to a +4. So that'll help you out with 22. Okay. All right, that's all good review. Let's see. We're going to be coming back to where we left off on page 14, but let's go to the end again, and let's look at these types of reactions and finish that up and then come back. So this is on page 18. So on page 18, these are some examples of single replacement. And where is the single one? Right here and right here. So these single replacements are always oxidation reduction. Always, always, always something is changing oxidation state from one side to the other, because a single element by itself does not have a charge. So you've got a chunk of zinc, you've got copper wire, no charge. Okay, let's look at these down here. What do we got? What type of reaction do we have here in A? Decomposition, right? You've got one reactant, two products. So you got decomposition. And is this oxidation reduction? We've got +2, -2. That makes that carbon right there a +4. And we still have +2 and -2, and we have +4 and -2. So that is only decomposition. No oxidation reduction. Nothing is changing. Let's go to the next page. Is letter B oxidation reduction? Absolutely, for sure. You've got something sitting here by itself. What is this charge of gallium by itself? 0. What's the charge of bromine here by itself? 0. Then bromide is -1. So this makes this gallium +3. And what type of reaction is this? Synthesis or combination. And it is also oxidation reduction or redox. And always look for what's being reduced first. That's reduction, right? This is reduction, which makes this the oxidizing agent. Oxidizing agent. I'll put OA, oxidizing agent. Whatever is undergoing reduction is the oxidizing agent. And then, of course, this is oxidation, right? This for sure is oxidation. And if that's undergoing oxidation, this makes this the reducing agent. What we got for letter C? Do we have oxidation reduction? Absolutely, for sure, 100%. How do you know that? Well, oxygen's sitting here by itself. What's the charge of oxygen by itself? 0. Whoa. I guess I threw O. threw a curveball at us here. This is 0. Hydrogen right here is +1, oxygen's -1. But there's a problem with this compound. Well, it's not a problem, it works out perfectly. This is hydrogen what? This is hydrogen peroxide. It's the only way for this to work. So what you have here is you have the only way for this to work is to be peroxide. +1 +1. Remember, peroxide is O2 -2. And if that's O2 -2, then these oxides are -1 each in peroxide. Why is there a -1 sitting right here? This is a 2, right? Why did somebody throw a pencil or something at me, yell at me? This is a -2, right? In water. +1 -2. All right, so here's what we've got. In the peroxides, one of these is going to a -2. It's going from -1 to -2. That's my reduction. And one of them is getting more positive. It's going from -1 to 0. That's my oxidation. All right, in letter D, what do we got? What type of reaction is letter D? This is exactly this week's lab. This is a precipitate. This is double replacement, double displacement, or metathesis. All the same thing. Double, what the heck? Drubble? Drudel? Druddle? It looks like drudel. Druddle. I wonder if that's a word. Double replacement. So double replacement here should not be redox. And if we go through everything, there's no charge. This is not oxidation reduction or redox. Okay, now I'm just going to backtrack and finish this up in order. And we're going to review acids, bases as we backtrack. So now we're going to go back to where we left off on page 14. Okay, let's review. This hydrofluoric acid is a weak acid. It is a weak electrolyte. You get a few ions in solution. You know it's a weak acid, there's going to be double arrows. 7% of these hydrogens come off or ionized. 7%, not very many. That's a very large number for a weak acid. That's a tremendously large number for a weak acid. Most are way, way down to 1%. Okay. We know that acids are going to produce H3O plus or H plus. We know bases are going to produce OH minus. Okay. Strong acids, HCl, HBr, and HI. Then we have, and you just got to memorize those three, HCl, HBr, and HI. Then the key is this. These are strong, and I think I mentioned this in a recording, because you have two or more oxygens than hydrogens. That's kind of a cheater rule. So if it's an oxyacid, if you've got 2 or more oxygen than hydrogen, it's a strong acid. Then I have write the ionization of perchloric acid. And I didn't do it there, did I? Why didn't I not do it there? I did hydrochloric. Well, that's all right. We just changed it to HCl. That's fine. Because we did HCl. Okay. It says, no, H2SO4 is a diprotic acid because it has 2 hydrogens that can ionize. H3PO4 is a triprotic acid because it has 3 hydrogens that can ionize. The first ionization of H2SO4 is 100%. The second ionization is way, way, way less. So it says, write the first ionization for H2SO4. So it's going to be H2SO4. It's going to be aqueous. One-way arrow, 100%. So 100% of this first hydrogens comes off or ionizes. So remember, this is coming off as an H plus, a proton. It's gonna attach itself to neutral water. So we are going to get H3O plus aqueous plus HSO4 minus aqueous. %. This is battery acid, sulfuric acid. So the battery acid that powers your battery in your car is a third. It's diluted down to a third. Sulfuric acid concentrate is very wicked stuff. Now it says write the second ionization. So if we're going to write the second ionization, we're going to start it right there. We're going to start with this hydrogen now that can come off. Double arrows. Very few of these hydrogens are going to come off. Very few. But if they do come off, we are going to get H3O plus again. And if an H plus comes off, we're going to be left with SO4 minus 2. This would then be a weak electrolyte. Very few ions, very few ions for the second one. Okay. So this is called ionization if you see plus H2O on the reactant side. Review. The most common weak acid is vinegar, acetic acid, written as HC2H3O2 or CH3COOH. This is the hydrogen that we say is the acid. This is the hydrogen. I probably shouldn't use pink, but that'll work. Okay, it says write the reaction for this acetic acid. If it is a weak acid, very few hydrogens are going to come off. Let's write it as now, when we wrote formulas of acids, if I said write the formula for hydrogen acetate, same thing, acetic acid, hydrogen acetate. So a few of these hydrogens come off right here. Plus H2O, liquid, double arrows. If an H plus comes off, we are going to get H3O plus. And then we are going to get C2H3O2 minus. If you have a weak acid, you are going to get few ions, few ions. Okay, the most common weak base is ammonia, which has the formula NH3. If you know you have a weak base, it is a good idea to write water as HOH. Write the ionization for ammonia. It's a weak base. If it's a weak base, we know we're going to have double arrows and we're going to get a few ions over here. But instead of getting H3O plus, since it's the base, we have to get OH minus, right? We have to get OH minus. So we would have NH3 plus HOH for water. If you know you're going to get a base, it's good to write water as HOH. This time, water acts as the acid, and H plus comes off of water. If an H plus comes off, we're going to end up with NH4 plus plus OH minus. This is ammonia cleaner, or Windex with ammonia. And we get a few ions. All right, so now let's put this all together. Neutralization reaction. Neutralization. We're going to have an acid plus a base. We're going to get a salt and water. And I have considered what happens when a typical antacid, such as malcolm magnesia, an aqueous suspension of magnesium hydroxide, is ingested to ease symptoms associated with excess stomach acid, HCl. So this is my acid, but we're still going to do this as double replacement. So if we do this as double replacement, hydrogen takes the place of the positive magnesium, And we would get HOH. And magnesium takes the place of hydrogen. Still double replacement. This is an acid plus a base. What do we get? A salt in water. Here's another one. This is HCl. This is the works toilet bowl cleaner or Lysol. If you've got that at your house, don't buy that ever again. The works toilet bowl cleaner, just don't buy that stuff. Or Lysol. If it says hydrochloric acid, 12%, don't ever buy it again. Because this HCl will leach out of that container as a gas. It's going to attack the hinges and your wherever it's stored. And if you have it there, your hinges are going to be all rusted. It is wicked stuff. But you can take the works toilet bowl cleaner and you can take sodium hydroxide drain opener, very wicked strong acid with a very wicked strong base. And if you neutralize it perfectly to a pH of 7, you can drink it because you just have salt water, right? For sure, this is a neutralization. You have an acid plus a base, and you get a salt and water. Double replacement yet, though. Now, if we wrote this out, the complete ionic looks like this. And if we crossed out our spectator ions, notice this is what we get. The H3O plus from the acid and the OH minus from the base just simply makes water. So this is the net ionic equation for any strong acid plus a strong base. You're just making water. Another way you might see this is H plus and OH minus. Okay. All right, now I think we're getting to the end of OWL. The last part of OWL in chapter 3, part 2 goes through reactions. So it looks like this. If you have a non-metal oxide, now a non-metal is going to be I generically put a Y in. So this could be a carbon, it could be a sulfur, it could be a nitrogen, some kind of non-metal. If you react a non-metal oxide with water, you are going to form an acid. So here's a generic, here's some examples. Carbon dioxide plus water, we make an acid, right? Sulfur trioxide plus water, we make, here's sulfuric acid, here's carbonic acid. Non-metal. Non-metal oxide, right? A non-metal with an oxide with water, when it reacts, you're going to get an acid. Okay, it's the opposite on the next page. On the next page, a metal oxide this time with water forms a base. How do you know you have a base? Hydroxide, hydroxide, hydroxide. So what do we got here? Those are metals, right? Calcium and sodium. Metal. And of course, an O is always an oxide. And what is OH minus? This is hydroxide. Which makes a base. Okay, I have this final summary. Here's a final summary I typed up. Let's look at this. Acids will produce H3O plus hydronium ion or H plus hydrogen ion or a proton. Bases will produce OH minus or hydroxide ions. Strong acids are going to ionize 100%, which means how many hydrogens are going to come off of the acid? Every one of them, correct? Every single one. Weak acids typically ionize less than 5%. You're going to see double arrows then. How many hydrogens come off of a weak acid? Typically less than 5 out of 100. Strong base, metal hydroxides dissociate 100%. Weak base, metal hydroxides dissociate way less than 5% again. Weak bases typically ionize plus HOH or H2O. Very little. So we'll do this one right here. Ionization of nitric acid. And then we got to stop. Is nitric acid a strong acid? Yeah, because you have 2 more oxygen than hydrogens, right? So what's that going to look like? HNO3, H2O liquid, one-way arrow. We're going to get H3O plus, and we are going to get NO3 minus. Okay, with that, you can do 1 through 27. I can only add 1 to this. 1 through 27. Print off chapter 4 because we will finish everything up for this chapter for sure next time we meet, which will be Friday. We are in March already.